Carrying on. Think you could do the same thing by cases on that next one? Yeah, just think about what the claim would become if A is positive or negative or 0. That looks like it could be done by cases, depending on whether A is bigger than 0 or less than 0. What about this one? What do you think the reasonable cases are for 5? Well, there are variables A and B, right? If they're both positive, then is it easy? If they're both negative, then is it easy? If one is positive and one is negative, then is it easy? In fact, let's be explicit. If A is positive and B is negative, then is it easy? Yeah. So I think there are like 4 cases, both positive, both negative, A bigger than 0, B less than 0, and the opposite. And maybe there should be some or equal to's in there. So that's like 4 cases. It's more cases, but not unreasonable. So you could prove that one just case-wise. Absolute value of B inverse is equal to absolute value of B inverse. That look like we could do it by cases too? Yeah, I guess you need to like argue that if B is negative, then so is its inverse. If B is positive, then so is its inverse, but otherwise I think that's okay. 7. That looks like it could be done by cases too. Either A is bigger than or equal to 0 or less than 0. And we will do that one by cases. The triangle inequality. Let's think about what cases you would need if you were to use cases. Because I want to convince you why we're not going to. So I guess it matters whether A is positive or negative. Whether B is positive or negative. So that's already like 4 cases. And whether or not A plus B is positive or negative. And so like, that's already up to 8 cases, which seems like too many. And they like interact, right? If A is positive and B is positive, then A plus B can't be negative. So really there aren't all that many cases. But I think there would just get to be a lot of tedium in dealing with it. So we won't use case-wise proof for the triangle inequality. Version 2 of the triangle inequality, does that look like you'd want to do that case-wise either? I think it'd be hairy, right? Like, you care about whether or not A is positive, whether B is positive, and whether A minus B is positive, but also whether the absolute value of A minus B is positive. So that was already like 4 yes-no questions. So that's like maybe 16 cases, but they'll interact with each other. So I wouldn't want to do that case-wise either. So with that out of the way, let's start proving some of them. Let's do the easy ones first. So I think that like all of these could theoretically be done case-wise. They could all theoretically be done case-wise. But I think for those ones is most appropriate. Once you get below that, it gets difficult. Anyway, let's try to prove claim 4. Let's try to prove negative A is less than or equal to A is less than or equal to absolute value of A for every A in this ordered field. So start with the setup. Let F be an ordered field. Let A be an F. There are 2 cases. Either A is bigger than or equal to 0, or A is less than 0. And let's maybe off to the side walk in each case. So we want to show negative absolute value of A less than or equal to A less than or equal to absolute value of A. And let's start with this. If A is bigger than or equal to 0, then what does this inequality become? What's the absolute value of A if A is non-negative? A. So this inequality becomes negative A less than or equal to A less than or equal to A. Are one of those two just like true automatically? And as long as we're just like sketching, I don't need to write all the logs. That one's obviously true. So I just need negative A less than or equal to A. If A is bigger than or equal to 0, why should those two be in the order they are? Well, I know A is bigger than or equal to 0, right? So I know that that's true. If A is bigger than or equal to 0, what can you tell me about negative A? It's less than, or maybe equal to. Right? A could be 0. You know, we could just do 0 as a special case, but I don't think I need to. Oh, do we have some result that says that if something is less than or equal to something else is less than or equal to something else, then the other two things are in that order? Remember the name for that? Transitivity. And is that like a full proof in that case? Yeah, so it's like half of the proof of half of the claim. So this sketched in blue right now is already a quarter of the proof. Oh no, there's no if and only if. That's a half of the proof. There are two cases. Either A is bigger than or equal to 0, A is less than or equal to 0, and in each case we must conclude absolute value of A with a negative sign, less than or equal to A, less than or equal to absolute A. And the spirit is just going to be, in each of these cases, see what that inequality becomes. And that's what we did, right? If A is bigger than or equal to 0, absolute value of A is A, negative absolute value of A is negative A, and the claimed inequality amounts to the inequalities negative A less than or equal to A less than or equal to A. One of those two is obviously true. I guess in the order I wrote it, it's the second one that's obviously true. Anything is less than or equal to itself. Since A equals A. To see the other inequality, notice that since A is bigger than or equal to 0, negative A is less than or equal to 0. So we actually proved the result that says that that's true, right? We wrote down the result that means that's true. We did like multiplicativity for inequalities. And so we could cite it now if we wanted to, but I'm going to start following the mindset that as we start proving these really foundational properties, I'm not going to cite anything for them because that would just make the document a slog in terms of checking which thing I'm citing each time. And I'm going to hold you all to the same standard. If you're saying, well, since A is bigger than 0, negative A is less than 0, that's okay. After you've actually done the homework set on inequalities. All right, let's carry on. By transitivity then, what done? Do you think the other case seems like it should be pretty similar? In fact, should I actually write any? Should I just pause and let you fill in the other half of the proof? Would people like me to keep talking? All right, I'll just be quiet for like 2 minutes. I guess I have to flip to the next page at some point. Cool. All right. Let's just talk through the blanks. In case 2, a is less than 0, so the absolute value of a is? Cool. So the claimed inequality, the one we need to prove, amounts to what inequalities?
D is greater than or equal to A. A is greater than or equal to, I mean, A is less than or equal to A.
Yeah. So negative a less than or equal to a. Okay. Yeah. And a less than or equal to negative a. Is that what they two boil down to?
Yeah.
Okay.
So I didn't write negative A, I just wrote A.
Yeah, great, because what is negative a? So in fact, if you just jump down to this, I'd be happy. One of these two is automatically true. Which one? Is a truism. Maybe what I want is negative a equals a. And now I'll put it on. You know, exactly how the proof goes up to you. To see the other inequality, I need a less than or equal to a. And right now I know that a is less than 0. Strictly less than 0. So if a is strictly less than 0, what can you tell me about negative a? Yeah. In fact, I'm going to say strictly greater than, but what you said is true too. I guess if you follow what was written instead of what should have been. Does that mean that? Does that give us the desired inequality? Sure hope so. So a is less than or equal to. Maybe I'll say, right, we care about the or equal to, so let's do that. That argument feel pretty okay? Nice. And you just break it down one case at a time. The next one in the list is claim 7. And the actual claim is on the previous page, so this is when it's really helpful to have a good, strong statement of what we want to show and what the assumptions are. Let F be an ordered field and A and B in F. We must prove that absolute value of A is less than or equal to B if and only if negative B is less than or equal to A is less than or equal to B. So there's my goal. And let's see, it's an if and only if. So that means you need to prove 2 implications. So there are going to be 2 halves to this proof, and that's where the cutoff is between those 2 halves. Let's start in on the first. Let's assume absolute value of A is less than or equal to B. I need to show that negative B is less than or equal to A, and that A is less than or equal to B. And here's one remark to start with. Absolute value of A is bigger than or equal to 0. And that is claim 1 of this proposition, which is something that you all will prove. And we even kind of sketched the proof already, didn't we? It's case-wise. Since absolute value of A is bigger than or equal to 0, and B is bigger than or equal to 0, then B is bigger than or equal to absolute value of A. Then what does transitivity tell me? B is bigger than or equal to A, and B is bigger than or equal to absolute A. A is bigger than or equal to 0, so.
B is greater than or equal to 0.
Cool. Nice. So I will again make a case-wise attack here. Either A is bigger than or equal to 0, or it's negative. Oh, and I don't want to use the same clause here. So there are going to be these 2 cases again. Here's where case 1 is, and here is case 2. So we'll break it up by cases. Either A is bigger than or equal to 0, or A is less than 0. And my goal is those 2 inequalities in each case. And I think maybe I'll go through the first case, and then we'll say the second half is going to be basically the same, unless people want me to go through the detail. Let's talk through case 1. In case 1, so in the case that a is bigger than or equal to 0, what can you tell me about absolute value of a? So here is the thing we get to assume. Absolute value of a is less than or equal to b. What does that assumption tell me? Oh, nice. That's like one of the claims. So we're halfway done. What is left? We need to get negative b less than or equal to a. Well, recall. Well, maybe we'll like sketch the idea first. Right now, I know that a is bigger than or equal to 0. And I know that b is also bigger than or equal to 0. So those two things on that side of that inequality, is one of them obviously positive and the other one obviously negative? Oh, sorry, I should be more careful. Obviously non-negative and obviously non-positive. Yeah, so 0 is between them, and I think transitivity will do the job. So b is bigger than or equal to 0, so negative b is less than or equal to 0. And by assumption, 0 is less than or equal to a. Oh, cool. Does that just do negative b less than or equal to a? Yeah. That completes the proof of this implication in this case. If a is negative, do you think a lot of that will be basically the same? Yeah, like there will be a double negative step, just like we saw in the previous proof. But otherwise, it'll be the same. So I think I'm going to skip the other case. Oh. And let's do the reverse implication. So on the other hand, let's suppose that negative b is less than or equal to a is less than or equal to b. Let us show that a is less than or equal to b. This also looked like we could do it one case at a time. I hope so. Let's try it. So either the thing in the absolute value is bigger than or equal to 0, or it's less than or equal to 0. There's one case. There's a second case. Apparently both of those cases will take like 2 sentences. And let's just go through the walk of at least one of them. So, yeah, first case first. In the first case, if a is bigger than or equal to 0, then what can you tell me about the absolute value of a? Cool. So the inequality we need to prove, there's the thing we're trying to prove right now. What does that inequality become? Oh, goddamn. It's the second case. But the same thing. So there's the inequality we want to prove. What does that inequality now become?
A is less than or equal to b.
Oh, is that just like one of the assumptions? Which is true by assumption. And maybe like it's helpful to add like a silly seeming clause after that, since we assume negative a less than or equal to b less than or equal to a. Neato. That seem all right? Do you think the other half of the proof is going to go the same? Yeah, just about. I think there will be a negative sign that appears, but that's fine. People feel pretty okay about this case-wise approach? Cool. And all right, whenever you see like a case-wise function that you're proving something about, cases. You'll probably need them. Let's close with the proof of the triangle inequality. And as I said, I'm not going to use a case-wise approach this time. So let's do this. Maybe we'll even go off to the side. So what is it that we want to show? We want to show absolute value of a plus b less than or equal to absolute a plus absolute b. Oh wait, is that like a proof that absolute value is less than or equal to a number? I think so. And that's, I think, is claim 4 what I want? No, claim 7 is what I want. So by claim 7, this is equivalent to saying that negative absolute A plus absolute B is less than or equal to A plus B less than or equal to absolute A plus absolute B. Do people see how claim 7 implies that? And we're just going to use different variables because I think it helps to. Right, there's claim 7 with different variable names. So it looks like I'm using star equal to absolute A plus B. And triangle is absolute A plus absolute B. That help? So I feel like I'm going kind of in reverse of how the actual proof will go. There's the thing I want to show. Claim 7 says that's the same as this. So let's try to convince ourselves that this is true. Do I know that A is less than or equal to absolute A? Do I know B is less than or equal to absolute B? Do I know that if you add inequalities together, you get a new true inequality? Yeah, that's one of the things that hopefully we at least wrote down in the last set. What about this fraction then? I guess if you distribute the negative sign to it, that seems helpful. Is negative absolute A less than or equal to A? Yeah, that's like claim 4, right? Is negative absolute B less than or equal to B? Yeah, okay, cool, there's the proof. Of course, we did it like backwards. We said, here's the thing we want to prove. Claim 7 says it's the same as that. Distributing the negative sign says it's the same as this. And now we know that that should be true by claim 4 and like properties of inequalities. But now let's go the other direction so the logic is actually correct. So let's start with claim 4. We use that negative absolute A, less than or equal to A, less than or equal to absolute A. And by claim 4, we also know that negative absolute B less than or equal to B, less than or equal to absolute B. We can add these inequalities together using the additive property of inequalities, which hopefully that's the right citation. We could check it. No, maybe I'll even pause. You look like you're interested in checking it. Cool. This would be even easier if this were like the online copy of the PDF because this PDF is hyperlinked. So I could actually click there and it would go to it. By the additivity property of inequalities, I can add this inequality to that inequality. to see that negative absolute A minus absolute B less than or equal to A plus B less than or equal to absolute A plus absolute B. Feel pretty good right now? And remember, in this sketch which we did beforehand, the whole goal is going to be getting negative stuff less than or equal to A plus B less than or equal to the same stuff but not negative. So I think I just need to factor out a negative sign, which we do have a combination of results that say we can do. Negative parentheses absolute A plus absolute B less than or equal to A plus B less than or equal to absolute A plus absolute B. Does claim 7 now apply? Yeah, I guess it goes this way. At least we're using that direction, but claim 7 is an if and only if. So, by claim 7, this is equivalent to absolute A plus B less than or equal to absolute A plus absolute B. Oh, was it doing this silly, like, focus in, focus out thing constantly? Oh, okay. That's weird that it would just do it the once. It shouldn't do it ever again now. Okay. So, what do people think about that proof? Seem sensible enough? And let me just point out, it would be like really annoying to do all of that by cases. We could have, and like when in doubt, when you don't see like another logical path, you know, you can try the like beating your head against the wall path to a proof. And it's not long, it's just not elegant. Groovy. So, with like 15 minutes left on the clock, 14 minutes left on the clock, I'm going to point out that the homework for today is really quite high. Prove 2 more of those claims. And since I think we managed to do it in class, did that feel slow or did that feel too fast? Okay, it felt acceptable. I bet you could prove these 2 using similar approaches in less time than it took to do in class. In fact, I think this is the type of homework where it'll take more time to like compose your formal write-up than will it take to write down your boss version of the proof. Let's start in on the last property in what the real numbers are. So we've said the real numbers are a complete ordered field. We've described what a field means. We know what it means for a field to be ordered. We haven't said what completeness means. And this is the one that will maybe feel the most abstract. And it'll also take the longest to get to the actual definition of completeness. But it's all about upper bounds. So let's start with this definition, which hopefully will feel very natural. Let F be an ordered field, a subset for, and X be a subset of F. An upper bound for X is an element U in F such that, well, you tell me. Maybe I'll start with an example and then we'll get a definition. Give me an upper bound on that set. How about 7? Is everything in that set less than 7? Yeah. So 7 is an upper bound, but so is like 6. And what would you say like the best upper bound for this set is? 5. Keep that in mind. That'll have to do with the word completeness soon. So an upper bound for a set is anything that's at least as big as everything in the set. So let's just write down that in terms of quantifiers and stuff. For a subset X, an upper bound for X is an element U. I'll use U for upper bounds just because of the letter U. Such that for all X in X, X is less than or equal to U. Does that seem like a reasonable definition for an upper bound? Yeah. It's something that's bigger than, at least as big as anything in the set. And it's important that I have a less than or equal to there. or equal to will be allowed. A lower bound. What do you think I would change to get a lower bound for a set?
For all x and x, x is greater than or equal to L.
Yeah. You want a single thing that's at most as big as absolutely everything in the set. A set is called bounded above if it has an upper bound. It's called bounded below if it has a lower bound. It's just called bounded if it is both bounded above and bounded below. And we'll write down definitions that look exactly like that at least 3 more times in this class. And we've got enough time. Let's build some intuition. Let F be an ordered field, A and B be an F. Let's just think very intuitively. Here are some sets. Do these sets seem like they should be bounded above? Bounded below, neither, or both? What seems like a reasonable upper and lower bound? Closed interval from A to B. What seems like an upper bound on that set? What's something that's at least as big as everything in that set? B. Yeah, I was going to say A, but A would be like exactly 1. So for this thing, it seems to have an upper bound. B is an upper bound. Is there anything else that we could write down as an upper bound for this set?
Plus 1.
Yeah. So here's the takeaway. Upper bounds aren't unique. If you find one, you can find infinitely many because you have an upper bound. You can keep adding stuff to get more upper bounds. If you wanted a lower bound, what would you say? A will do. So A minus 1. The set of all x in this ordered field for which x squared is less than or equal to 1. And notice, the claim you're about to make would be one that we kind of want to prove. But just thinking intuitively, what seems like something that should be an upper bound on that set? Should it have an upper bound? Yeah, let's even just think visually for now. This is like the squaring function. I want numbers whose squares are at most 1. Oh, does that look like a free image? Am I taking a free image right now? Yeah, so it's like I want everything for which the output is in that range. Yeah, that looks like it's negative 1 to 1, doesn't it? That look like it should have an upper bound? Lower bound? Cool. What about the whole field? Should that be bounded above? Folks who would want it to be bounded above? Folks who would not? Yeah, that makes sense, right? You can't find a number that's bigger than every other number. In fact, if I told you that 5 was an upper bound, you'd say, no, 6 is in the set and 5 is not bigger than 6. So it's 5 isn't an upper bound. If U is any upper bound, U plus 1 is a problem. So not bounded above, I bet you could do it by contradiction. And maybe we'll jump to here. This one is logically interesting. Is the empty set bounded above? Think for a second. And people would want the answer to be yes. How many people would want the answer to be no? Right. So, those of you who said yes, do you have an upper bound in mind?
0.
Let's try 0. And then we'll see how much we care about what number that is. All right, so let's think about what we need to prove. We need to prove that for everything in the empty set, that thing is less than or equal to 0. How many things are in the empty set to check? None. So we have to check a yes-no statement, a true-false statement, for no sample points. It's just vacuously true. I think that's how you spell vacuously. I know vacuum has 2 U's, but I think that's how you spell vacuously. On the other hand, maybe let's try to be, maybe you don't think that's formal enough. Let's try to prove this again in a different way. Let's try contradiction. So let's suppose 0 is not an upper bound. Now let's think about what that would mean. That would mean it is not the case that for all x in the empty set, x is less than or equal to 0. How do you feel about negating statements like that? How do people feel comfortable with that? How do people feel uncomfortable with that? All right, well, let's just talk through it slowly. So we are saying it is not the case that from every possible sample point something happens. That must mean there is a sample point where it doesn't happen. So this is equivalent to there exists an x in the empty set such that not x is less than or equal to 0. That feel reasonable? If it is not the case that for every element of the set a thing happens, then there must exist a counterexample. Sorry, this room is a tragedy and I don't know what to do with this. It used to be that I could like flip over the screen, but then they put up a sign that told me to stop, and when I didn't, they put it on a leg. Oh, and I know what it means to negate this inequality. So that means there exists an x in the empty set such that x is bigger than 0. There's a contradiction. There's nothing in the empty set. Yeah, I think that's the symbol for contradiction that most people in this room like more. Nice. So we'll continue talking about upper and lower bounds and properties thereof. Maybe I'll just give you a tour of this set, this particular set of notes to see what some takeaways are. So there's this idea of upper bounds. And we've seen like some like idea of a best upper bound. If I would be like the best upper bound that tells you the most for this set. We will make up a name for these things called supremum or least upper bounds. And we'll also do the opposite. There's a greatest lower bound, which is also called the infimum. We'll do some stuff with those. There's the definition of complete. An order field is called complete if every set that is non-empty and bounded above has a supremum. And what that kind of means is if you have a set and you can find things bigger than everything in that set, then there should be like a least thing that's bigger than everything in the set. Which like if you visualize the number line, like that should happen. And if it doesn't happen, then there's like something missing from the real numbers. They're incomplete. That's why this property is called completeness. The final axiom will be the real numbers form a complete or revealed. And with that, I'll stop. I'll see you all on Wednesday. Unless anyone's coming to my office hour, which is in 1 hour, all right? Anyone coming to my office hour today? See you there.